Hi everyone, welcome back to another video. So in this video, we're going to be talking about the equation that you've probably all seen, which is the I is equal to C times dV over d. Sometimes you might see it written about the multiplication symbol, dV over dt. And sometimes you might even see it written like this in terms of the delta symbol. All of them basically meaning the same thing, which is that the current is equal to the capacitance times by the change in voltage over time with respect to time. So when I first heard that, I didn't know what that meant. I don't know if that made sense to you, but let's break it down, okay? Okay, so we're talking about capacitors, right? So first, let's break down probably the most confusing part of this part, which is this. What does this actually mean? When you see this whole equation, it just means the rate of change of voltage with respect to time. So what does the whole equation mean then? What we're saying is that the current flow into a capacitor, i.e. this thing, talking about current flowing into it, is equal to the capacitance, which is this value here, multiplied by the rate of change of voltage over time. Right, so capacitance is obviously measured in farads, right? So it's F symbol. The rate of change of voltage refers to, for example, the voltage being applied going up by 1 volt per second, or by 1 millivolt per second, or by 10 millivolts per millisecond. Right, so we're saying that the voltage being applied to the circuit or just to the capacitor is going up or down, and it's doing that by 1 volt per second, or maybe 1 millivolt per second, or maybe 10 millivolt per second, etc. So what we can say is if this dV that we're talking about over dt, which remember is just the rate of change of voltage with respect to time, if that is a large amount, right? So let's say, I don't know, it was 100. You're saying it's 100 volts per second. So the larger that we make this amount, what we're saying is that if we have a capacitance value of 4,700 microfarads, we're saying we're multiplying that by 100 over 1 second. So the larger that we make this value, the larger the current is going to be, right? So what we're saying there is that if the voltage is changing rapidly every second, every millisecond, whatever, then the current flowing into that capacitor is going to be a large amount. This I here is going to be large. What we're also saying is that if this is a small amount, so for example, you can just do this equation yourself, right? Let's say we take 4,700. We'll just remove the microfarads for now. 4,700, and we're going to multiply it by 10 over 1. You've removed the second there, right? So which number is going to be larger? We're talking about this is going to be the current, right? So 4,700 times 100. So this equation here is going to lead to a larger current, and this is going to lead to a smaller current. So what we know is that if the rate of change of voltage is large, then the current entering the capacitor is large. Conversely, if the rate of change is slow in terms of the voltage changing, then the current flowing into or out of the capacitor is also going to be slow or small. So if we was to actually graph this, what would it look like on a graph? So if we assume that this bottom bit here is time, so if we say that we start off at this point here, 0 seconds, and then say 10 milliseconds, go through time, right? We assume that here is voltage, max voltage, and also current. Okay, so let's start off with voltage first. As we start to apply voltage to the circuit and the capacitor gets charged up, we're going to see the voltage go up like this until it reaches its max. And then obviously the capacitor is not going to get a higher voltage than the voltage source, right? So if you've got, for example, a 9-volt battery, it will reach 9 volts up here and then just level off, right? So what's going to happen in terms of the current? Remember, the current is equal to the capacitance multiplied by the rate of change of voltage throughout time. So the current's going to start off high. It's going to start off at the top up here. And you're going to see the maximum amount of current being drawn from the circuit when we start. Then as time goes on, the current's going to fall slowly up until eventually it reaches zero current and then levels off just the same as the voltage. So once the capacitor is fully charged up here, the current flowing through will be zero. So this is an important point to understand. So at this point here, the rate of change, which we said is dV over dt, is equal to zero. So if you use your calculation, we know I is equal to C times dV over dt. If we replace dV over dt with zero, that gives us I is equal to C times zero. And obviously anything multiplied by zero is zero. But let's just say we've got a capacitance 4,700 nanofarads. Then multiply that by zero, then I is equal to zero. So as we can see here, at this point in the circuit here, when the capacitor is fully charged and the rate of change, the voltage isn't changing, it's zero, then the current down here is zero. Alright guys, thanks for watching. I hope that helps, and I shall see you in the next one. Peace.